Lecture 29, we shift our focus from the subatomic nucleus to the largest continuous objects in the universe, stars. In spite of the extreme difference in scale, in size, this is a logical segue, for stars are nothing more than giant nuclear fusion reactors. For most astronomers, the great principle associated with this lecture on astronomy would be that stars are giant nuclear reactors. But I want to take a different tack. I want to focus on the nature of astronomy itself. The fact is that most people love astronomy, but few people realize that astronomy is the science and the art of collecting and analyzing and interpreting photons from space. I'll begin this lecture by focusing on the nature of astronomical data. What are astronomical data? What can we learn from them? How are these data collected by telescopes, and what are the great telescopes on Earth and in space that are now in use and are now being constructed? Then and only then are we going to examine the nature of stars. Our study will be greatly enhanced by the simple and elegant Hertzsprung-Russell diagram. This diagram reveals that most stars obtain their energy by the fusion of hydrogen. Let's begin then by considering a connection between this lecture and the last. Nuclear fusion reactions are the process by which two hydrogen nuclei come together, combine to form helium, plus lots of energy. And the amount of energy that's produced is exactly correlated to the amount of mass that's lost by Einstein's famous equation, E equals mc squared, a relationship between energy and mass. Now, astronomers tell us that stars are natural fusion reactors, but how can they know that? We can't go to the sun and sample it. We can't send probes into its atmosphere, or they'll burn up. So how can a scientist say for sure what's going on deep inside a star? To answer those questions, we first have to examine the nature of astronomical data. Astronomy is first and foremost an observational science, and virtually all the information we have about distant stars comes from photons, that is, electromagnetic radiation that travels at 186,000 miles per second through space. The art of astronomy then is to collect and to analyze and to interpret these photons, these data. And that's what astronomical data is. Astronomers measure photons, and in particular, they measure four different properties of photons. They measure the wavelength of photons. They measure the intensity of the photons arriving at Earth. They measure the direction in space to those photons, and then they measure the variation of those three properties, wavelength, intensity, and direction, as a function of time. A star may get brighter and dimmer. It may move against the backdrop of the space. Now, wavelength is measured by spectroscopy. For example, a prism breaks all light into a spectrum of different wavelengths, the different colors of light. By the same token, you can measure all the different wavelengths of different kinds of electromagnetic radiation by different techniques. There are radio waves, there are microwaves, infrared, visible light, then the ultraviolet, the X-ray, the gamma ray. And for each of those different wavelengths of electromagnetic radiation, you can measure the wavelength through spectroscopic means. The intensity of photons is measured by a device very much like a light meter. Remember the photoelectric effect. As a photon comes into certain materials, it actually triggers an electron jump. An electron can leave an atom and then flow through the material like an electric current. One photon causes one electron, two photons cause two electrons to move, and so forth. And the level of current that flows through the material is a direct measure of the number of photons that are coming to us. And so we can use the photoelectric effect as a way of detecting the intensity of these photons. The direction is measured by two angles. You can measure the direction of an object in space by first taking a compass and measuring the number of degrees around from north on the horizon. And then the second angle is an angle from the horizon up to the object. And those two numbers provide an indication of the position of that object. And of course, since objects move, you also have to record the exact time that you've made your observation. And finally, astronomers document the variation of wavelength and intensity and position with time, because all objects in the heavens change. They get brighter and dimmer. Their wavelengths may change, and indeed their position in the sky changes. And so these are things we have to measure. Now, in order to do this well, you need measurements of ever greater accuracy. The more accurately you can measure wavelength and intensity, the position and the variation, the more you can understand about the heavens. Well, what do we learn from these data? From these data, astronomers attempt to understand the spatial distribution of objects, their dynamic state. They try to understand the past of the universe and the future. Now, a major challenge in astronomy is that the universe is, in fact, a three-dimensional volume, and yet the backdrop of stars that we see looks to be two-dimensional. So, what do we learn about stars? What can we say about stars? It turns out there are at least 6 key pieces of information that we can glean about the stars from our observations. We can, in fact, measure the distance to many stars, and I'll talk about that in a second. We can measure their composition, what atoms they're made of. We can measure their motion, how they're moving with respect to the backdrop of stars. We can measure their temperature. We can measure their brightness, and we can often measure their mass. Let's look at these 6 characteristics of stars. The first, the distance to an object can be measured in a number of ways, but the most basic is called parallax. That's a form of triangulation. Now, the sun is the center of the orbit of the Earth. The Earth goes around the sun with a diameter of orbit about 186 million miles. So over a 6-month period, the Earth swings from one side to the sun to the other, and then back again. And so our position with respect to the stars keeps shifting back and forth. And as it shifts, closer stars appear to move more than the more distant stars. So therefore, for stars that are up to perhaps 10 light years away, we can actually see the variation in the position of the star and measure its distance directly by triangulation. We also can use standard candles as another way of measuring distance. These are stars and other objects in the heavens that have a known brightness. If I held a candle in front of you and you knew how bright that candle was, and then I walked some distance away, the candle would get dimmer and dimmer, but you could tell how far away I was just by measuring the brightness of that candle. And by same token, we can tell how far away many stars are by measuring the brightness of them. The second parameter, composition. We can often measure the composition of a star by looking at its spectrum. Recall that different chemical elements emit lines, bright lines, when electrons rise to higher energy levels and drop back down. They emit photons of characteristic wavelengths. So hydrogen has one set of characteristic wavelengths, helium another, calcium another. And so by looking at the characteristic spectrum of stars, we can actually determine the composition of those stars, even though they may be millions of light years away. The motion of a star can sometimes be detected by absolute motion over short periods of time. From year to year, some stars actually appear to move slightly, and so we can say how they're moving in the skies. But there's also a method called the Doppler shift, by which we can measure the movement of a star because of the change in the wavelength of those characteristic lines I just told you about. Any object that emits waves will display this behavior of the Doppler effect if it's moving toward you or away from you. If an object moves towards you, the wavelengths come more quickly, they pile up, and so you see a shorter wavelength, a higher frequency, a blue shift of the light. And so the characteristic hydrogen lines are shifted towards the blue part of the spectrum. If the object moves away from you, the wavelengths are spread out towards the red end of the spectrum, and we see a red shift. The degree of the blue shift or the red shift tells us the relative velocity of the star to us. The surface temperature of a star, how would we determine that? Well, it turns out that's pretty simple. It's just basically the color of the star. And you've all seen this. A very hot flame, for example, in an acetylene torch looks blue-white. A candle flame is more like a yellow flame. And as you have a fire that's slowly dying, with embers cooling down, they become orangish, and they become reddish and darker and darker. Well, that's a reflection of the temperature of the material. Redder materials are cooler. Blue-white stars are very hot stars. And you have all gradations in between. Just by looking at the color of a star, then, we can determine its temperature. Now, the brightness of a star, how bright it appears to be, combined with the knowledge of how far away the star is, gives us an indication of the total energy of the star. So brightness becomes a very important thing to measure. This is called the apparent magnitude. And the apparent magnitude is directly related to distance and energy of that star. And finally, the mass of a star can often be determined just by looking at its motion, especially if you have a binary star system. Most of the stars in the heavens include one star rotating around a second star. And that rotation motion can often tell us the mass. However, most of our information about the mass of stars comes from the theory of how stars form and how they burn. Well, that's the data. Now, how are data collected? That's a key part of science. And of course, astronomers' principal tool is the telescope. You've undoubtedly seen many photographs of remote observatories in Chile and Hawaii and so forth. And telescopes, in the most general senses, are then devices that collect photons from space. The science of astronomy has gone hand in hand with the development of new telescopes, new kinds of telescopes, and improved larger instruments. Many astronomers refer to the present age of astronomy as the golden age of astronomy, because for the first time we now have satellite observatories, telescopes in space that can measure all the different wavelengths, X-rays, gamma rays, radio waves, and so forth. Let's think about the different wavelengths and about what instruments are available to astronomers to study each of those. This is the real meat of the science of astronomy. Well, optical telescopes are the most familiar, and they use a combination of lenses or mirrors to concentrate and magnify light from different objects. Recall that it was Galileo Galilei who in 1609 was the first person to use a telescope trained on the heavens. He used that telescope to discover the craters of the moons of Jupiter, the rings of Saturn, and so forth, and marvelous original discoveries. Now, his telescopes used lenses, a combination of lenses through which light was bent. But as you make lenses larger and larger, the glass gets very heavy, and you really reach a limit beyond which a lens can get no larger. And when you get to this point, you need to start resorting to mirrors, curved mirrors to focus the light, because the mirror can be very thin and still be reflective. The largest telescope used mirrors of this type, sometimes mirrors more than 25 feet in diameter. There's a new technology that allows you to make these mirrors on a giant rotating wheel. The whole wheel is a furnace. It melts the glass, and then as it spins, it causes the glass to form a beautiful curved surface, a perfect mirror curved surface. There are other ways of doing this too. There are new multiple mirror telescopes that have lots of cheap small mirrors that are all precisely aligned by computers. Now, the best astronomical observatories for visible light are constructed at very high elevation. That's far from the light pollution of cities and far above most of the atmosphere. There are many important observatories. The Keck Observatory in Hawaii, for example, is one of the largest telescopes. There's a wonderful cluster of telescopes in the high mountains of Chile. The optical components of a telescope are only part of the story. Old telescopes, classic antique telescopes, are often refurbished with new detectors. And so not only do you have to concentrate the photons, you have to collect them, you have to detect them. The classic way in the 18th and 19th century was to use your eye and just to write down in a notebook what you saw. And then the Herschel family introduced photography. And photography and astronomy dates from about the middle of the 19th century. That was a wonderful way of collecting photons. Today, most detectors are electronic. They record individual photons hitting a plate and record the position of those photons. Much more sensitive to film, and it allows you to do wavelength resolution as well. So while you're collecting photons, you're determining the wavelength of those photons. It's really a major advance in astronomy. Space telescopes are the instruments of the future. We have the Hubble Space Telescope, which is providing an unparalleled view of the universe in optical wavelengths. You may recall that the space telescope had to be repaired in a spectacular space rescue mission, but now it is by far the greatest telescope that has ever been built, and there are wonderful dramatic photographs being made all the time. By the way, the telescope's last servicing mission will be in 2002, and it's expected that that telescope will be a very active and useful instrument at least through the year 2010. The Hubble is going to be surpassed, though, we hope in 2007 by NASA's new generation space telescope, which is predicted to have a mirror which is 8 to 10 meters across, up to perhaps 30 feet across, an incredible mirror. And that mirror is going to collect lots of photons. It will be by far the greatest telescope that anyone has ever used, seeing the farthest reaches of the universe. Also in the books are two optical interferometric telescopes. These are telescopes that synchronize the measurement of photons from two widely spaced mirrors. And the idea here is you don't collect as many photons, but you get incredibly accurate positional measurements. You can find the position of very small objects. And so with two mirrors separated by 100 meters floating in space, we might actually be able to resolve planet Earths around distant stars. This new NASA telescope is called the Planet Finder. It's scheduled for launch in about 2010, and it's going to be incredibly exciting when that goes up. Now, there are telescopes in place today that also measure all the other wavelengths of electromagnetic radiation. The atmosphere is largely transparent to radio waves, so radio telescopes can be based on the ground, and that's a good thing. Radio waves are so long, you need a very large dish to collect them. There's two strategies here. One of them is to have one huge dish, for example, the Arecibo Observatory in Puerto Rico, where one dish fills an entire valley. The other option is to have lots of smaller dishes that form an array. For example, the very large array of radio telescopes in Socorro, New Mexico. That gives you a much longer baseline and allows you to resolve much smaller objects in the heavens. Extending this idea to the extreme, there have been various times when radio telescopes around the world have been linked to photograph one object. And in this case, you have a 4,000-mile or more baseline, which gives very high resolution to the outer reaches of the universe. As we go to other radiation, other wavelengths, we have to have other strategies. Now, short wavelength microwave radiation can be studied from ground-based telescopes, but there's a great deal of interference, especially from communication. So here it's best to go into space. Much more sensitive microwaves were provided by the Cosmic Background Explorer, NASA's COBE satellite, which was a satellite-based microwave observatory. And there are several new microwave observatories that are on the books. One to be launched in 2002 by NASA. In 2007, there's a joint European-US microwave observatory called Planck. These satellites are going to map slight variation in the cosmic microwave background, which I'll talk about in the lecture on the Big Bang, about the origin of the universe. We have infrared observatories. These reveal warm objects in the heavens, things like dust clouds, young stars, even planets. Any object that's relatively cool emits infrared radiation. Now, the problem here is that the atmosphere is just chock full of infrared radiation, so your satellite has to be above the atmosphere. And indeed, the satellite itself, the detector itself, emits infrared radiation. So you have to cool that detector down to liquid nitrogen temperature or colder. This means you have to carry your coolant along with the spacecraft, and all of these infrared satellites have a short lifetime. The infrared astronomical satellite, that was IRIS, was launched in 1983, and it operated for about 9 months before it died. There's several new cooled satellites. One of them, Certif, is an advanced satellite to be launched in 2002, and it probably will last about 5 years with improved coolants. Now, X-rays are also absorbed by the atmosphere, but X-ray telescopes are really interesting because X-rays are highly energetic, and X-ray telescopes reveal some of the most energetic events in the universe. The first X-ray satellite was the Röntgen satellite launched by NASA in 1990, and it studied the brightest X-ray sources in space. Now, right about the time I'm giving these lectures, NASA is talking about launching another X-ray satellite, the Chandra X-ray satellite, and that's going to be launched to image X-ray sources, actually find out where those X-ray sources are coming from in the sky. And then in conjunction with that, there are two other satellites, X-ray satellites, that are being launched by Europe and Japan to measure the wavelength of those X-rays, because it's hard to measure the position and the wavelength of X-rays at the same time. I hope you're getting a sense. This is an incredibly exciting time in astronomy. We are living in the golden age of astronomical observations. Never before in history has the pace of discovery been so rapid or the instruments been so sophisticated. So the newspapers almost every week will have a story related to these discoveries. Finally, the most energetic events in the universe are gamma rays. And one problem with gamma rays is it's very hard to focus them. They pass through our bodies. They pass through almost any satellite you can make. So it's difficult to detect gamma rays, but there are even new satellites that are planning to do just that. So this is an incredible time to be an astronomer. Okay, now that we've reviewed the nature of astronomical data and the great photon collectors of our time, we can begin to think about stars themselves. When we turn our telescopes to space, most of what we see are stars. We see billions of stars in our own Milky Way galaxy, and then we see billions more galaxies beyond, each of those with billions of stars. Carl Sagan's billions and billions is right on target. It's an amazing universe out there. Some systematic sense of all these stars can be made on a graph, the Hertzsprung-Russell diagram, which is a graph of temperature versus the total energy output. The Hertzsprung-Russell diagram is an amazingly powerful tool. The surface temperature, which is plotted on the horizontal scale, is measured by the color of the star. This is a very well-established technique in industry, by the way. It's called optical pyrometry, where you measure a color and you determine a temperature. The horizontal scale is actually plotted as 1 over temperature, so the Hertzsprung-Russell diagram is a little funny. The cooler temperatures are on the right-hand side, the hotter temperatures are on the left-hand side, but this nicely spreads out the known stars on the diagram. On the vertical scale is the total energy output. And recall that you measure the total energy output of a star by knowing both its distance and the amount of light that's coming to us, its apparent magnitude. So if you think about a candle that's 10 feet away as opposed to a candle that's 100 feet away or 1,000 feet away, the candle looks dimmer. The total energy output of that candle is constant wherever it happens to be, and that's how we think about stars. The vertical scale, by the way, is a logarithmic scale. It's a factor of 10 orders of magnitude from top to bottom, because there's so many different kinds of stars, some extremely energetic, some hardly putting out any energy at all. One of the nice things about the Hertzsprung-Russell diagram is it makes no assumption whatsoever about a star's energy source, about its history, about its future. But you start seeing intriguing patterns in this diagram. It turns out that the great majority of stars lie along a prominent curvy band right down the middle of this diagram. Stars lying close to this diagonal band are called main sequence stars. When you look at main sequence stars, you see a very close relationship between temperature and total energy output. You have relatively cool main sequence stars, stars that are red in color, with very low surface temperatures of around 3,000 degrees centigrade, and they also have very low energy outputs. On the other hand, you have very hot stars, stars with surface temperatures of tens of thousands of degrees that have huge energy outputs 1 billion times greater than the cool stars. There are also 2 other common sequences, common groupings of stars on the Hertzsprung-Russell diagram. In the upper right-hand corner are relatively cool stars that nevertheless give off huge amounts of energy. These stars have been termed red giants because the only way that a cool star can give off huge energies is if it's very, very large. At the bottom left of the Hertzsprung-Russell diagram, on the other hand, there's a group of stars that's extremely hot, surface temperatures of tens of thousands of degrees, but giving out very little energy, perhaps only 1,000th the energy of our sun. And the only way that can happen is if the star is very small, has a very small surface area. These stars are called white dwarfs. The power of the Hertzsprung-Russell diagram is that it uses simple, measurable properties of stars to compare and contrast the whole variety of stars, whether they're very close or very far away. And what you see is clear patterns. The patterns emerge from this diagram. In science, anytime you can start seeing patterns from a chaos of data, you're well on your way to using the scientific method. You make observations, and then you see the patterns. That leads to hypotheses and theories. This is the same way that Mendeleev approached the periodic table of the elements. And we see this happening now with the pattern of stars. We now know that stars begin their lives as spheres more than 90% hydrogen, with a small fraction of helium and other elements. And astronomers soon realized that all of those main sequence stars, the majority of stars of all the different sizes and temperatures, obtain their energy through hydrogen fusion, the process called hydrogen burning. And I want you to think about how a star might burn. one of the things is think about the relative lifetimes of stars, a big star versus a small star. Well, it's surprising. It turns out that very small stars, because the interior generates so little heat and pressure, take a very long time to burn. The fusion process is so slow that these stars in the lower right-hand portion of the Hertzsprung-Russell diagram can take hundreds of billions of years to burn. And the largest stars, the ones that are so incredibly hot, have temperatures and pressures so high that they burn up exceedingly fast. The stars, in fact, can disappear in a matter of 100 million years or less. So the biggest stars burn the fastest. The hydrogen fusion process that provides stars with energy takes place in 3 steps. First, you have 2 protons that fuse together. They quickly undergo a beta decay, and that forms a deuterium atom. So you have 2 protons, they come together, 1 proton becomes a neutron, and you get a situation where you have a deuterium atom, a proton and a neutron together in the nucleus. In the second step, a proton and a deuterium come together to form a helium-3 nucleus. A proton gets combined with a proton and a neutron. You have 2 protons and 1 neutron in the nucleus. That's helium-3. Finally, 2 helium-3s collide together. They form a helium-4 and 2 protons fly off. And so in those 3 steps, 4 protons have fused to form a helium-4 nucleus, 2 electrons, 2 neutrinos, by the way, and lots of energy. This hydrogen burning process is extremely well documented from a theoretical point of view, but one aspect is still not at all well understood, and this is a great mystery in astronomy today. The sun and other hydrogen burning stars have to produce prodigious amounts of neutrinos. Those are those very light, perhaps massless particles that are produced in certain nuclear reactions. When scientists go to measure solar neutrinos streaming to us from the sun, they only measure about 1/3 as many as they expect to see. And this is called the solar neutrino problem, which you may have read about in the newspaper. Now, neutrino detection is very difficult because neutrinos have no charge. They pass through most matter. But nevertheless, we have techniques to measure neutrinos, and we don't see enough. One possible solution is that solar neutrinos may oscillate. The oscillation of a solar neutrino to other kinds of particles could explain the missing neutrinos, but it would require that neutrinos had mass, because by the arcane laws of particle physics, the only way that you can transform from one particle to another is if you have mass. If neutrinos have mass, that has profound implications for the future of the universe, which I'll talk about in another lecture, Lecture 32. To summarize this lecture, we've seen that astronomers collect photons. In particular, they measure 4 properties of photons coming to us from space. They measure the wavelength of photons, all the way from radio waves to gamma rays. They measure the intensity of those photons. They measure the direction of those photons in space. And then they measure the variation with time of wavelength and intensity and direction. And these data help us to understand 6 aspects of stars. They help us to measure the distance to those stars. They help us to measure the composition of the stars, their motion in space, both towards us and away from us and side to side. They help us to measure the temperature of the surface of the stars, the total brightness of the stars, which then gives us information about the total energy that that star is emitting, and finally, information about the mass of the stars. It's the great telescopes, both on Earth's surface and in orbit, that help collect this full spectrum of photon data, the electromagnetic data from the stars. Now, these data are summarized on the Hertzsprung-Russell diagram, which reveal that most stars, almost all the stars we see, result from the fusion of hydrogen to form helium and lots of energy. In the next lecture, we're going to examine our sun and the fate of our sun and other stars that lie along the main sequence of the Hertzsprung-Russell diagram. And as we shall see, the sun and all other stars have a finite lifetime.